So in computer science, we always seem to have debates when new stuff gets invented. So way back in the 50s, and somebody thought of floating point arithmetic. Such a radical idea. And why are people so lazy? You don't need floating point, you just need to scale your integers properly. And then in the 60s, and that's time sharing came along. And why are people so lazy? They want to sit in front of a terminal and get their answers back immediately when they could just put in a deck of cards and go away for a cup of coffee and come back in half an hour to discover they left out a comma, and so on. So it's always been like that. And the trouble is, every time you invent something new, it costs you something. So it's the same in logic. The thing I could do actually is switch off some lights if people would prefer that. Or is it okay that off or on? Sounds like people want something. Is that better? Okay. So when you have a simple logic, you can do much more. You can automate much more. So with propositional logic, we have super powerful tools for crunching these problems, really big problems like millions of variables. They can do stuff for us. And we'll see this later. On the other hand, it's just and or not. And even with a million variables, it's still just and or not. Sometimes you want a bit more expressiveness. So you say, let's add quantifiers we have for all and exists. Well, you don't have those great solvers anymore. We still have some fairly decent tools. Again, we'll cover them later. You can add further stuff, and actually now we're getting beyond the course, and we're also starting to get beyond what you can automate reasonably well. So, and this is the real tension now where people working with formalisms, they say, we need this wonderful expressive formalism, but then you struggle to make the computer do anything with it. Now, it is true, we're computer scientists, and our job is to make the computer do our work for us. Whatever the thing is, if the complaint is that it puts too much work on the computer, that's not a complaint at all. That's its job, right? It's meant to work. They are really fast and powerful. However, some things are just undecidable or they're just, can't reasonably done, in which case we need to find another approach. Anyway, today we are going to switch to first-order logic. Everything will get a bit harder, and we'll kind of see that the way we actually build proof procedures for first-order logic, at least some of them, will involve kind of trying to reduce it to propositional logic again. So, and I think we even saw this last year in discrete maths. So it means that we have in our formalism for all and there exists. And it also means what I have on this slide, so I'm contradicting my own slide. The other thing we now have for first-order logic is we can talk about functions. So instead of just and or not, this is true and that is true, whatever, suddenly we can have functions. No father takes an argument, returns a result. Here, cousin, it's a relation, takes two arguments. It's true, maybe, if they're cousins. And now here we've stated a kind of inference, if you like. It says if X and Y have the same grandfather, then they're cousins. So you see, you can express things quite neatly. We can also see some limitations of this. According to this, you're your own cousin. You probably never thought about yourself in that way. And your brother or sister is also your cousin, and so on. So never mind. That's always a problem with mathematics. If any of you have ever come across Greek logic, you'll have seen this particular inference here, which seems to be the cliche version of Greek logic, the syllogisms as they're called. It looks pretty trivial. Here you have all men are mortal is a kind of quantifier, but they're doing it in natural language, so it's a mess. Now, why do we call it first order logic? What's first about it is that our functions and our relations are talking about a fixed set of individuals. So, for example, let's say literally people. So in this case, we're talking about people and their mothers and fathers and cousins and so on. But we cannot talk about, let's say, all sets of people are something, because if you want to talk about sets, you're going into the higher orders of logic. Now, Lewis Carroll, of course, was a logician. That's why, and you can actually tell if you read Alice in Wonderland and Through the Looking Glass, you can tell he's a logician. There are little hints all over the place. He made a big book of syllogisms. So I have some examples here. I'm sorry to say, because all these examples involve generalizations, and most generalizations tend to slide into things one shouldn't say very quickly, so I had to select very carefully from Carroll's syllogisms. If one finds the whole book, you might find it very entertaining, but I wouldn't take it too seriously. They are only logic puzzles, right? They're not meant to be true. Now, you see what I have, one of the reasons I put this here is not just to be dumb, but there are different kinds of conclusions one can draw if you do it in the Greek way, which, thank God, we are not going to do after this slide. So if you learned logic long ago, before the formal era, you had to memorize these combinations of things like all, some, apparently works, none, some, and this is a negative one, and that's a negative. You know, this is how logic used to be done before we had quantifiers and formal rules. So if you find the formal stuff awful, just be glad you never had to learn this. There are, I believe, 27 valid combinations of syllogisms, and you had to memorize them all or think them up. And you imagine being examined on that. Okay, what I'm going to give you now is the syntax and semantics of first-order logic. I hope it will be straightforward enough. So, in first-order logic, again, syntax is all I'm talking about for them. We have terms and we have formulas. What are terms? Well, variables are terms, constants are terms, and if I have the right number of terms for a function, then I can apply the function, and that's a term. Kind of big deal, right? It's trivial, right? An argument function, in particular, a zero-argument function is a constant. Here I have a function applied to n terms built up in the same way. Big deal. The thing about the language. So typically, you choose your problem domain. You then adopt functions and relations according to your problem domain. If you're talking about people, you'll be talking maybe about mothers and fathers and cousins and so on. If you're talking about numbers, it will be addition and subtraction and greater than and less than. So mathematicians will talk about first-order languages because you can just choose the language you want depending on what you're interested in talking about. Formulas are the things that are true or false. And at the bottom, the most elementary formula is a relation like, x equals y or cousin xy. In general, a relation symbol can have n arguments. Let's say a color might be just one argument. So red of x means that x is red. Has one argument. It's not so easy to think of a natural three-argument relation, but I don't know, something like something is the greatest common divisor of x and y, that's three arguments. Anyway, once you have relation symbols, you can apply it to the correct number of terms. Of course, terms were on the previous slide, so we know what they are. Now I have a basic formula. It's called atomic because it's the smallest formula there is. It's a formula that cannot be broken down. So there's nothing to do with radiation here, although I'm sorry to say that some people who worked in this field got carried away, and soon they were talking about electrons and all kinds of nonsense. But not here. So once we have our atomic formulas, we can build them up using and or not, etc. We've got formulas. Quantifiers, in fact, turn out to be optional, but only for about 5 minutes. I made a silly diagram. I'm sorry, you see, I had to do all this when I was pre-recording last year, and since I only have one projector, I think instead of drawing circles and doing this, I'm just going to stick up this thing. What does this crazy thing mean? It took me a moment to remember. I'm just trying to summarize on one slide what all the stuff we've got is trying to do. So this big circle represents our universe of values, all the individuals we're interested in. So in the circle might be all the integers, if we're talking about integers, or all the people we're interested in, all the colleges of the university, all the countries of the world, etc. So this is our universe or our domain of discourse. Constants we expect to denote individual elements. Functions are maps that clearly map the universe into itself. That would be a one-argument function. And a relation, so P, this is a one-argument relation, so it just represents a subset of the universe. Okay, another brief aside. Merely to say you can do something without quantifiers at all, and the only reason I'm even mentioning this, there's only one reason, which is one of the most important theorem provers ever built takes this approach. So there's a thing, it used to be called the Boyer and Moore theorem prover in the 70s. And then eventually they decided to give it a name, so they called it THUM, T-H-M, for theorem. And then they changed the name to NQ-THUM. And then they changed its name to ACL2. They made a new version. They're all very quirky. They all have Lisp as the implementation language and a pure version of Lisp as the actual logic. Any of you even know Lisp? No. It's a relic of the era of APL, Snowball 4, and all those things. Although it's a lot cooler. I used to teach it. In the 80s, I taught it here. If you were 30 years older, you'd be learning it. Anyway, quantifiers complicated things, and they found that they could do a lot of quite cool things, like, let's say, proving the equivalence of this function here and that function there without using quantifiers, although they had various tricks to do that. And the cool thing about it, and their logic, again, at risk of making too many asides, this is really a very important system, and in particular, everything in their logic is executable. Now, this is actually very weird. So normally, in mathematics, you can write stuff which is not computable. And loads of the things that we write, you're talking about complex numbers or something, that you have no hope of computing it because, you've got infinite stuff there. So they managed to make a logic in which everything is computable, This is actually, because I mentioned a couple of lectures ago, these constructivists that some people are following constructive logic, which is much closer to computation. Their system is so much closer than that to computation that everything they do can be simulated, and so they've made a niche for themselves in hardware verification where you can write the hardware in their logic, you can prove stuff about it, and you can then execute it all in the same framework. And they didn't pay me to do this plug for them. It just is a very important thing out there. However, our quantifier-free days are over. You've seen quantifiers before, I'm pretty sure, in discrete maths. And if you've done a maths course, of course, you'll have used them. But remember, we are using quantifiers in a strictly formal way. That is, these are symbols of our calculus. If you're in the habit of writing for all and exist simply to abbreviate English and to save you the trouble of writing out the words for all and there exist, I advise you not to do so on this course when you're doing an exam or something, because it will look like you made a mistake, right? So just write them out. For us, these are reserved symbols. Most of this stuff is routine. There's one thing that could trip us up, and I do need to mention it. You will recall from that page from Whitehead and Russell I showed you, I think, last time, that there were lots and lots of dots on it because they didn't believe in parentheses. Those dots have almost all disappeared except for this one. This is a vestige remaining of Whitehead and Russell. If you see a for all or exists followed by a dot, remember the dots replace parentheses. The dot means the scope of the quantifier is as far as it can go. Now, why am I mentioning this? So in this course, I have tried consistently to use this notation here, in which quantifiers bind tightly and you have to put brackets around the body. The problem is, in my day-to-day work, I always use that one. And in fact, in the world of theorem proving in general, most people use this one here. And you see, it's very easy to get tripped up because the logic textbooks, as well as my notes, give a very high precedence to the quantifier. And if you don't notice the little dot, you're going to read everything wrong. Of course, it's a big clue. If you see some Z's over in B, it's a clue that maybe Z is, that other Z is probably in the scope of the quantifier. Because it's really nasty to kind of use the same variable, both free and bound, in the same formula. Okay, anyway, some obvious stuff here if you have never seen quantifiers before, and I hope that none of you have. But you see, we can express things like all men are mortal now, using a combination of implies and for all mothers are female. And then I don't want to explain this. There exists a unique X satisfying A. You can see there exists X, A satisfies A, and for every Y that satisfies A is equal to X, and so on. Now, the reason we don't have to memorize 27 combinations of for all and exist and figure out which ones imply something and which ones don't is because we have rules for all, for implies, for and, for or, and so on. And those existing rules combined in the way they normally work will give us all of those 27 things. I don't even know what they are. And to help memorize them, there's some connection with the name Barbara. I'm not joking. I am not making this up. Somehow Barbara helps you remember which syllogisms are valid and which aren't. So as I said, be glad you weren't doing this course in the early 19th century. But then they didn't have computers then. See, logic is everywhere you look. Now, we've had the syntax of first-order logic. Now, the semantics is going to be a little unpleasant, so I should just remind you why. More generally, it's not just that I like making people suffer, but in mathematics in general, it involves setting up things and then interpreting them in weird ways. So I actually have to go to the trouble to say that probably this thing which we write as 1 is actually going to denote the entity which I'm going to call 1 because, I don't know, you could write it in another font or something like that. But in general, things can mean very surprising things. And generally in mathematics, especially if you look at something like group theory, you might find that the 1, let's say in a group, does not refer to a number at all. So, I don't suppose any of you come across group theory? One or two. So a group in mathematics, it's a set. One of the elements of the set is called 1. There is a product. For every 2 elements of the set, you can form their product, and you can form the inverse, and this product is also associative. What is that good for? Well, one thing we never do with groups is say, okay, yes, you could look at the non-zero real numbers, and yeah, this is just a multiplication. That's inverse, that's normal reciprocal, that's just the real number 1. BFD, right? Where it's interesting is where, for example, the set is not the set of non-zero reals, but, for example, rotations in 3 dimensions. The unit rotation means not to rotate. The product of 2 rotations is you go like this, and then you go like that. The inverse is to rotate back. That turns out to be a group, and that turns out to have something useful to say about chemistry. Now, I know nothing about chemistry. It's molecules rotating in 3 dimensions. I know nothing about chemistry, but I'm told that is an application. Another application has to do with permutations. Remember, a permutation is a bijective function. You had that in discrete maths. There, the unit is the identity function. The product is the composition of 2 functions. And remember, if a function is bijective, it has an inverse. Now, this so-called permutation group turns out to be super important, and I believe it is used in Galois theory and showing that 5th-degree equations don't have closed-form solutions, things of that sort. So, in general, in maths, we are mapping symbols to unexpected things. Okay, so to do this, and so this is going to give us the semantics of first-order logic. Actually, you've seen the semantics of much more complicated languages last term. Never mind, and actually, I can promise you this as well, although we're going to go through this because I think you need to know that there is a semantics. We're not going to do much with it. So, first, we have to interpret the constants, and I hinted at this already in the first lecture. So, when I talk about an interpretation, it will be a domain, which is, remember that circle I had, wherever it was, it's here. So, an interpretation is just telling us the set, which is this circle, and it has to be non-empty, and it has to give, for every constant, it has to designate an element of the domain. For every function symbol, the interpretation gives us an actual function over the domain. So remember, F here is only syntax. The meaning of f is a true mathematical function. Likewise, for relations, the symbol p is only syntax. The meaning of p is some Boolean valued function taking n arguments. So again, having had semantics already, that should, I hope, be straightforward for you. Now, I said we don't use it much. Where I do use it, you will note on exam questions going back to year dot, they often will say, prove or give a counterexample. The counterexample will look something like that. Doesn't have to be super technical, but a counterexample to a formula will say, well, the domain is this, and the constant could be 0, the function could be that, and then say that is a counterexample to the thing I'm trying to prove. So you will find this is very frequently, almost every year, is something that comes up on the exam. Okay, we have variables as well. So for variables, we need a separate part of the interpretation. So remember, father of y is a variable. And by the way, there's a convention we will invariably see. Beginning of the alphabet, like ABC, those are constants. End of the alphabet, X, Y, Z, they will be variables. And in a sense, we have to give meanings to both of them. But the idea of constants is that, okay, you have to set them up once, but at that point they stay constant, right? That's why they're called constants. Exactly like, why are these called variables? Well, I won't tell you, because they vary. Anyway, we have a separate map giving the values of the variables. Now, the meaning of terms is done in the completely obvious recursion. Okay, I've written it out mathematically just to show you I can do it, but this is the absolutely obvious recursion you would expect. The meaning of a variable comes from this valuation v. The meaning of a constant comes from the interpretation we had in the previous slide. The meaning of a function application for that, remember f is syntax. In fact, the whole thing inside the brackets is syntax. So you have to grab the meaning of the function, which is an actual function, recursively evaluate all the terms, giving me now n elements of the domain D. I apply the function to those n elements, and bingo, this denotes some other element of the domain D. So a guy named Alfred Tarski was the guy who first wrote out the definition of truth in first-order logic. And yeah, it is just semantics, as you've seen already. And the reason for it, back when people started doing this stuff, let's just say in the 70s, they weren't very rigorous. And if they had a for all and it exists, they thought, yeah, I got it. Whether they were doing the right things with them didn't seem to have a lot of priority with them. So there was a lot of lousy work done. So we need to know what these things really mean. Okay, I've already given you how we denote the semantics of terms, and they will be values of the domain D. For the semantics of formulas, remember formulas are true or false, so we will get a 1 or a 0 as the semantics of a formula. Now, quantifiers will complicate things for us, and for this we need an ugly thing here. So remember, it's the variables that vary. So if I have a bound variable x, and I'm looking at the meaning of a formula that has a for all x or an exists x in it, I'm going to need the ability to adjust the valuation in order to plug in different values from time to time. And this is the notation I'm using here. Various notations are used, but this one says valuation v except that x stands for a. So this is a modification. So v was the original valuation. Now I want to update it and assign a into x, you could say. I do it like that. So this modified valuation maps x to a. Using this, we are now able to define our formulas. Okay, it looks gruesome, but really there's not too much going on. So remember, we've fixed the domain already. We fixed the interpretation, which is the meanings of the constants, symbols, the constant symbols, the function symbols, and the relation symbols are now all fixed. Now, separately, we have a valuation giving the values of all the free variables in the formula. And remember, we keep them separate because typically when you set up your application, your domain and your constants, functions, relations, symbols, their meanings will stay fixed for a long time, whereas the values of the variables will kind of vary very frequently. So that's why we keep I and V separate. And now we recursively say, and I'm only treating a few cases, for a predicate symbol, so I'm simplifying it just to one argument. In general, of course, there could be many. You just get the meaning of the term, which is the argument, the meaning of the symbol P. So now I have an actual map that will map this thing to 1 or 0, and if it evaluates to 1, then we call it true. That's where this satisfaction symbol from. If we have the relation symbol equals in our language, we don't always, but if we do have equals in our language, then we demand that it works. In other words, the semantics of equals must be the semantics that equals is supposed to have. So in this case, you get the meaning of T, the meaning of U, and we ask whether they are equal to each other. Now, around this point, you may have noticed that this great song and dance is just turning our logical symbolism into English, right? Equals, equals. I'm sorry about that. Semantics tends to do that. So the meaning of the formula A and B, so this A and B is syntax. So we recursively get the truth value for A and for B, and we combine them using, the English word and. And now the tricky thing, I mentioned on the previous slide that we need the ability to alter a valuation at a single variable, and that's what we're doing. So exists XA will be true, provided there exists some element of the domain, which I'm calling here M, such that if I plug in M as the value of X, A evaluates to true. So yes, the thing that bugs me about this, and maybe you, is that there's an awful lot of symbolism here, and yet it is really trivial. It's like that sometimes. If it holds for all valuations, then it simply holds, and we can leave that out, and we can just write the I and say that the formula is satisfied in that particular interpretation. If it is a closed formula, the jargon, a closed formula has no free variables. So if I have a closed formula, the valuation is irrelevant. It has no free variables, so the valuation is not going to affect. So then we can talk about the formula being satisfiable if there is some interpretation making it true. Okay, that is Tarski's truth definition. You see, the thing I like about that is if anyone ever asks you what is truth, you have the answer. And just show them that slide. Now, I mentioned a lot of this already. This is not examinable. This is merely here to show you what people had to do before. So yeah, I looked this up last year. Imagine this. Type every B is A. Some B is a what? So this is a kind of existential quantifier. No B is A. Some B is not A. And so I said 27, but there are in fact 24 combinations from which you can deduce something. Anyway, that's it for now. Find yourself a nice open fire, and I'll see you on Monday. Thank you.